Hello everyone, and welcome to our demo session on open machine learning tools in geological interpretation. In this presentation, we'll walk you through key problems that the industry is facing right now, comparison between human expertise and neural networks performance in ongoing projects, pitfalls of data science and exploration, and of course, profitability variety of different implementations of machine learning in production stages. I believe that GTC conference audience is very diverse. So after this brief introduction of industry's current state, we'll move on into detailed demo in Jupyter Notebooks. In the end, we will show QR codes and links to our blog where you can find more detailed information and of course send us any follow-up questions that you might have further. Thank you for joining us today. Let's start. It has been stated before that the nature of oil collectors has changed, and the software that served the needs of oil and gas industry faithfully are no longer suitable, since the oil is much harder to locate, estimate, and extract. Nowadays, deep learning algorithms have proven their extreme value in almost every sphere of life. And of course, all vendors started attempts to tame its power. At an early stage in oil industry pipeline, the cost of mistake has extreme influence on the project. It touches almost every sphere, from collector estimation, exploratory drilling, and every step that follows. As it had been stated before, by NVIDIA and Equinor researchers, human interpretations are visions, with educated guesses, and along that are time-consuming and subjective. And at the same time, the market of quality data science brains is extremely limited. And even though every computer science graduate calls himself a senior DS developer, we all know that is not true. This means that for each one proper data scientist invested, the best returns will be in the upstream sector. If you skip it and push hard on the later stages, you must know that you already missed your billions potential on mistakes and high uncertainty, non-corrected with machine learning, and there's no way to take that back. I believe all people in the industry are still in doubt. Is it actually worth it? Well, we went all the way through, and here's what we bring to the table. For each stage in upstream, we have assembled a dedicated library with everything ready to use. Pre-processing, models, metrics, monitoring, and all you want. This session focuses on two main frameworks, SeismicPro and SeismiQB. And to give you a taste of what can be achieved in a matter of days with this toolbox, we'll go through first, machine learning for field seismic data processing, developed in a ready-to-use set of tools for tasks such as noise attenuation, first break picking, spherical divergence correction, and more upcoming this year. And secondly, we'll talk about framework for deep learning research on 3D cubes of seismic data that allows to execute seamless data processing, solves tasks of seismic horizon extension and detection, and shifting development to more complex issues. For more info on our open frameworks collection, we will provide links at the end of this video. This should, once and for all, kill major myths in oil and gas data science business, such as nothing needs to be changed, geoscientists don't have to learn about machine learning, some random specialist can just throw some neural networks and start generating massive income for the company. And my favorite, old proprietary and expensive software can solve new era changes. All this we'll start to explain in seismic processing tasks.
The very beginning of oil and gas exploration is seismic surveying, when the raw data that represents the geology of the region of interest is obtained. This data is used to construct a geological model that allows making accurate conclusions about oil reservoirs in the area. In order to make precise geological model, the raw data needs to be denoised, cleaned, and structured, and that is the purpose of seismic processing stage. It consists of lots of iterative and routine operations performed manually by experts, which is time-consuming. Moreover, mistakes in seismic processing stage make seismic interpretation extremely difficult and leads to wrong estimates of oil deposits and their locations. Machine learning is the key to speed up seismic processing and relieve experts from routine, leaving them with the most interesting and challenging tasks. We've been developing a framework for deep learning on pre-stack seismic data for some time. It's called SeismicPro and is designed to enable easy and convenient training of neural networks for seismic processing tasks. Our framework provides tools to load, process, and visualize pre-stack data in various representations, such as raw traces, seismic gathers, semblances, and pickings. This allows one to apply a variety of processing actions and employ different approaches to train neural networks for a variety of tasks, like first break picking, denoising, velocity picking, and others. In this example, we'll talk about one of the initial steps of seismic processing, the first break picking. The task is to determine the time of the first signal arrival for each seismic trace. These times are later used to perform static corrections, the procedure that eliminates the effect of varying elevations in survey area. This allows to model seismic survey as if it took place not on the Earth's surface, but on some flat plane. When all the sources and receivers are located on the same level, the trace's coherence increases. This leads to a great effect. Static corrections can unveil. Now, knowing how important accurate first break picking is, let's get into action. We trained the first break picking model on the data from 3 surveys conducted using seismic vibrator sources. Our framework provides tools to combine a number of surveys to create a unified pool of data for training. The resulting dataset contains 300 common shot gathers, or a little bit over 277,000 traces. The test set contains 15 gathers and over 50,000 traces. Here, we load one seismic gather from the SeismiQB file, and in the next cell, we plot it to get familiar with the data and the labels. The top image shows the whole seismic gather, and the bottom one zooms into first 50 traces from it. The red dots on the plot correspond to the first break picking times. Note a distinct amount of noise in the traces before the first breaks. This is a typical artifact for vibrator sources that makes first break picking fairly difficult. Now, let's talk a little bit about the model. We have attempted to treat this task as a regression, predicting a single number for each trace, but that approach didn't show good results in our experiments. So we changed the tactic and started to treat this task as semantic segmentation, classifying each sample of the trace as a signal or non-signal one. We will use 50% of the data for training, and validation is going to be carried on a small labeled subset of a survey from an ongoing project. We are using a one-dimensional model that operates over each trace individually. We've been experimenting with two-dimensional models trained on crops of seismic gathers, but the resulting masks were imprecise. Among other options, one-dimensional segmentation showed the best results, so we adopted this approach. For semantic segmentation, we exploit ResUNet with attention model. This is basically the 4-stage UNet, where each stage of encoder and decoder consists of a single ResNet block, and at the end of each stage, there is a spatial channel squeeze excitation block for attention. You can easily define such complicated models and other training parameters with few lines of code using the model config. For example, here we also declare that we will use Adam optimizer with a learning rate of 0.001. In the next cell, you can see the training pipeline. In the first line, the model described in config is initialized. Then the traces and the picks are loaded. Following actions perform standardization of traces and conversion of picking times into masks. Next, the data is stacked, fed into the model, and the training step is performed. This model is trained for 1500 iterations with batch size of 1024 traces. And the whole process takes about 11 minutes on our current hardware. Those timings are important since it usually takes hundreds of such experiments to find the proper approach, model architecture, and hyperparameters. To stay on top of it, we write efficient code, experiment with cool software tricks, and keep track of the latest hardware to benchmark our pipelines. We have trained our networks on a variety of GPUs, both consumer and enterprise grade. Here you can see the speed benchmarks for out-of-the-box DGX A100 compared to a consumer-grade GPU. You can see that the training phase is almost 2 times faster on DGX, and this ratio still holds if we enable prefetch option, which allows to prepare the next batch on CPU while the current one is still being processed on GPU. On inference, DGX provides 30% speedup without prefetch option and 20% speedup when prefetch option is enabled. Take a look at the loss function plot. You can see that it has converged to almost near zero plateau. Now we can save the model and move ahead. Here is the inference pipeline. It consists of 3 blocks. In the first one, the model and the variables to store the predictions and the labels are initialized. In the next one, the data is loaded, processed, fed into the model, and the resulted masks are converged into pics. And in the last part, we store the labels and the predicted times to use it later. The whole testing pipeline processes 15 gathers with over 50,000 traces in a few seconds. In the evaluation section, you can see the model predictions. They are depicted as blue dots, while the red ones are ground truth pics. You can see a lot of outliers, and the mean absolute error on a new survey is more than 20 milliseconds, which is bad. The model often reacts to the noise that precedes the first breaks, and it seems that it lacks some prior information about neighboring traces. To fix this issue, we decided to apply two-dimensional post-processing using another neural network. Here, we use the same data as in the previous notebook, but now the inputs for the model are stacked predictions of 1D ResViewNet, and the labels are stacked masks from the previous pipeline. Validation is going to be carried out on the same partially labeled survey from an ongoing project. Let's load one batch to take a look at the data. This picture shows seismic gather, the second one shows stacked predictions of 1D model, and the last one, stack of ground truth masks. Here you can see the outliers in the predicted masks that we want to remove. The dataset is split in the same way we did in the previous notebook, but now the other part of the split will be used. The model is again a ResViewNet with attention, but now it has 2D convolutions, and each block of encoder and decoder now consists of 2 res blocks. The training pipeline is a bit more complex now. After loading the data, we use 1D model to obtain its predictions, then we process them and use to train two-dimensional model. Here we load 2 gathers on each iteration and generate 4 crops from each gather. This model is trained for 1000 iteration, and it takes about 12 minutes on our hardware. The loss also converges to almost zero. In the next cells, we can save the model and define the config to load it later. Inference pipeline is similar to the training one, except for a number of processing actions, like assemble of cropped predictions into the entire gather again for visualization. This whole pipeline takes about 20 seconds to process 15 gathers, and it's possible to use multi-GPU inference to get almost linear speedup. Here are the results obtained after neural network post-processing. The blue points are predictions of 1D model, and the green ones are predictions of 2D post-processing model. You can see that it has removed a great number of outliers. The mean absolute error has also dropped to less than 10 milliseconds, and that is not the limit. We are conducting experiments to improve one-dimensional model and remove the remaining outliers after 2D post-processing. In March, our system produced pics for a new project, and we found out that fine-tuning 1D model even on as little as 20 seismic gathers improves model performance. Labeling of a few gathers takes about an hour of expert's time and can be done seamlessly, since the data usually comes in a few pieces a few weeks apart from each other. An expert can label a few gathers from the first part, and then, if there are no extreme variations in subsurface conditions, apply the resulting model to other parts of the survey as they come. We also had a chance to compare our results with the ones made by a contractor. Geologists calculated brood stacks using both peaks and calculated correlation of a horizon in brood stack with the well data, which is basically the ground truth for the horizon's location. It turned out that correlation coefficient for model's predictions was 2% higher, and the standard deviation of error was 3 meters less compared to human peaks. Moreover, our system was 3 times faster, and we see the possibility to accelerate up to 8 times using CuPy and multi-GPU inference. This is only one of many seismic processing tasks that we are working on. Detection of errors in seismic geometry, acquisition footprint removal, noise attenuation, stacking velocity picking, and others. We also work closely with our experts to develop metrics for quality control and provide them with useful tools to validate models' results and verify that seismic interpretation can be carried out with the required precision.
One of the crucial steps in field exploration is creating a structural model. It consists of both horizontal and vertical reflections and can be used to make informed decisions about potential petroleum deposits underneath. Today, I will be mostly talking about the seismic horizon detection task, and we will use it as an example of applying machine learning to seismic interpretation. Seismic horizon is a boundary between two layers of rock, and it can be easily seen on any type of seismic data, even for a non-specialist. They are used to outline potential oil reservoirs and are essential information about the field. Naturally, during the exploration stage, seismic experts label a lot of seismic horizons for every region. Any mistake at this point leads to either underestimating or overestimating the amount of oil, leading to huge profit losses in either case. Our idea of applying machine learning to the seismic interpretation is as follows. An expert can label a small amount of data, just like a few slices, like 20 of them, and the neural network can extrapolate them on the whole spatial range. Now let's look at the example in code. It is a fully fledged notebook with whole pipeline of creating a very good horizon from tiny amounts of labels. It follows our standard of presenting results and thoroughly describes our datasets, the model training procedure, and how to apply it for inference. This notebook is readily available on GitHub, and we will provide links in the end of our presentation. We start with the inputs. You can see that most of the things are imported from our SeismiQB library. It is also open sourced on GitHub, and it can be used by anyone for the seismic interpretation tasks. We use it for fast data loading, model training, and evaluation of various seismic labels. Then we load the dataset with exactly one cube and one horizon. Imagine the cell number 4 shows the horizon surface from above. The color corresponds to the depth for each point in the field, and in the next cell we can see the front view of the same horizon. It is distinctly visible and clear. This horizon was hand-tracked by an expert. We will cut a very sparse grid from it and use a neural network to restore it to the whole spatial grid. But before that, we must discuss the method of assessing quality of detected surfaces for either models or experts. Without having a reliable metric, it is practically impossible to track progress of our neural networks. So we have developed a quality map that is computed by comparing each trace's labeling to a set of randomly chosen reference points. The greener, the better. As this horizon is trivial, the whole map bursts with green, and the yellow lines correspond to areas of faults or cube defects. On other horizons, on other fields, the metric can look very differently and allows us to make quantitative conclusions about surfaces. Note that computations are heavily vectorized and computed on GPU. By using CuPy, we sped up the entire process by a factor of 20 compared to the regular CPU computations. So, having a metric to evaluate our result, we can move forward. As I previously mentioned, we want to train on a very sparse grid cut from the original horizon. It is created in the cell number 7, and here is the top view on it. We can see that it consists of just a few slices of data, compared to thousands in the whole field. In real projects, our geology experts can label 10 to 20 slices in a matter of hours, so it is reasonable to test our model by cutting carcass like this. We generate data for our models in small patches cut along the carcass, and want model to predict horizon location from a raw seismic image. Here we can see the distribution of sampled data from a trained dataset. The rest of the field, which we can see here, can be used for validation and testing purposes. Next, we define a model architecture. It's custom encoder-decoder, which consists of dozen ResNet blocks with visual attention modulus, and it is roughly similar to deep lab architecture. In the same configuration, we define loss function, which is binary dice, optimizer, and learning rate scheduler. There is also a micro-batch key. It allows us to accumulate gradient over small portions of a training batch. Without that technique, it is pretty much impossible to train large models. By the modern standards, this is a relatively simple architecture. We got it as the result of a research over tens of thousands of various configurations. It is easy to iterate over them by changing keys and values in the same dictionary. We found out that some of the more sophisticated architectures lead to minor accuracy gains, but we believe that simplicity, reliability, and ease of interpretation are key in this task. In the cell number 11, we declare the plan of actions to be performed on each of the training iterations. First of all, we load both seismic images and segmentation masks, then normalize them and apply some augmentations, and finally we update model weights in the very last action. Running training pipeline takes just a few minutes, and the loss curve shows steady convergence. Despite it, we train model for a touch longer to allow batch normalization averages converge as well. To increase device utilization, we generate data in a separate CPU process while our model is trained on GPU. This is a native functionality of our pipeline class and controlled by prefetch parameter. It allows us to speed up our training procedure by up to 2 times. We also use mixed precision, automated mixed precision, and it allows to speed up the training procedure by another 17%. We have tested our models on different devices, and here you can see the comparison of a consumer-grade GPU and the DGX A100. The enterprise-grade GPU provides a massive speed up and also relieves memory constraints, allowing us to focus on model development. This result is achieved by an out-of-the-box DGX with no NVLink or other optimizations. A trained model can be used on the individual patches of test dataset, and we can see that model predictions look very good. Arguably, they are more cohesive than the ground truth. Predictions on small patches are not that useful though, and our goal is to make a prediction on the whole spatial range. To this end, we split the cube into crops, make a prediction for each of them, and stitch them together into one 3-dimensional volume, from which we can extract the horizon surface. It takes just a few lines of code to obtain labeling for 99% of the cube area. Our metric tells us that the horizon prediction is excellent, and it is actually better than the original one. For example, it does a better job with tracking the cube edges. On the other hand, some of the traces are not labeled at all, and while it can be fine in some places, for example, in area of faults, it is crucial to have a method of eliminating all of the holes in the resulting surface. Before doing that, we can compare our prediction to the ground truth, and we can see that they are very much alike. The only noticeable difference in labeling is on the left upper edge of the seismic data, which is expected. By now, we have been able to train a model to locate a particular horizon on raw seismic data. We used labels along a sparse carcass as a training dataset and have been able to predict the same horizon on the entire field. To eliminate holes and other small flaws, we apply an additional neural network as a post-processing step. It takes not only the raw seismic data, but also a part of the true mask and aims to predict the original mask. The data generation, 2 input images instead of 1, is the only difference between that new extension model and the one that we just looked at in the notebook. Adding it at the end of horizon detection pipeline allows us to produce almost perfect horizon surfaces. There is obviously more to seismic interpretation than just seismic horizons. Along with horizontal reflections, we need to track the vertical ones. Notably, the biggest difference to the horizon detection procedure is in the data generation. By changing our segmentation masks, we can train a neural network that accurately predicts faults and discontinuities on the entire seismic volume. The next logical step after creating structural model of a field, which consists of horizons and faults, is locating petroleum reservoirs in form of alluvial fans and underground estuaries. One more neural network applied along horizons does so, and once again the main difference is in the data generation step. A suite of our models allows to cover a huge part of the exploration pipeline. We have successfully tested the entire procedure on more than 20 fields with completely different subsurface geology, using metrics we have created to evaluate its performance. On the last of our projects, we were able to create a fully fledged structural model in a matter of hours. This is a massive speedup compared to months and even years taken by a team of skilled geologists. Our neural networks allow us to label virtually every voxel of seismic field, making a huge step towards eliminating uncertainty in petroleum production.
Here we can see our models at work on a currently developing field. Starting with a very sparse carcass that barely covers the area of a cube, we generate accurate and precise horizons on the entire seismic field. Despite tracking them individually, they never interlace and flawlessly outline subterranean layers. Such quality is necessary for excellent velocity models for petroleum location in the most complex areas of the Earth. We then add fault surfaces, tracking vertical discontinuities. Whole structural model is built in multiple processes in parallel, taking less than 2 hours in total. As a result, we get a pixel-wise understanding of field geometry and potential oil deposits. This was a brief demo of our toolbox for exploration on real-world data available for everyone on GitHub. If you still believe that synthetic data, outdated software, and poor engineered R&D models that have never seen the light of production environment can generate you massive income, you are probably beyond redemption. It may sound harsh, but it's true. Introduction to domain and industry overview can be found on our Medium blog. On our website, you can see more training sessions and digital books that we've created specifically for business. This May, we will hold an online event and show more frameworks in great detail. Thank you for joining us. See you soon.